like I'm zoomed in really close, but I think it's kind of helpful. All right. Okay, I'm assuming I'm recording. Yes. Ooh, I'm 6 seconds in. Okay, so 1.2 is vertical stretches and reflections. So reflections are like a mirror. The only two places you're going to reflect are in the x-axis or in the y-axis. So those are going to be like mirrors for you. So if my graph is over here and I reflect it in the y-axis, the image graph is going to look the exact same, and it's just going to be on the opposite side. So you're going to any reflection you're going to treat like a mirror. Quick question, did my y values change there?
No.
No, they're all the same height. I haven't moved anywhere. If my original one, my x values were negative, what are they now?
Positive.
Positive, okay? So when I reflect in the y, so y is my mirror, like treat it like a mirror. When y is my mirror, it doesn't affect y values, it affects the x values. So on that note, if I were to reflect in the x-axis, so again, if this is my original, do my x values change now? No. It's your y values. They were positive, now they're negative. So it's kind of weird, it's kind of opposite. If you are reflecting in the y-axis, your x values change. If you're reflecting in the x-axis, your y values change. If you think about it, it makes sense, but it's like, oh, if I reflect in the x-axis, then my x values change. That's incorrect, right? Because those would be your reflections. So reflections, we're just going to treat them like they're a mirror. So again, almost symmetrical. Your axis would be your line of symmetry, whatever axis you're reflecting in, and you would have the exact same image. Now stretches change the shape. I like to write, and I will tell you guys this, as you go on to post-secondary, I like to write little notes all over, quick things that will help remind me what makes sense. So you'll see, like, I'll put these at the top, like scribble stuff. That makes sense to me. If it doesn't make sense to you, that's okay too. These are your notes. I'm never going to look at them, so it's got to be what works for you guys. Okay, so with changing the shape, we did this yesterday. Remember, I had my original box P, perimeter, or like 2x2s. And then I stretched it. I said I had a vertical stretch of a factor of 2, so that meant I took my side, my original side, and I times it by 2, which gave me my new side, which became 4 units instead of 2. Does that make sense to everybody? So a stretch is going to manipulate the look of your original object, right? A slide or translation isn't. A slide just moves its location. A reflection just moves its location. It's those stretches that actually change how it looks. Okay, you guys remember this? Invariant points. What are invariant points? You guys are like, please don't look at it. They're the same point. Same point is shared by the original figure or the parent figure and the image, so the one that's changed. Okay, so an invariant point is a point that's shared. That's exactly the same place on the parent, is exactly the same place on the image. And the image is the one that we've done the changes to. So original figure or parent figure, that's what we're starting from. Remember, that's the graph or the equation. That's the first one, and then we do all this funky stuff and we create an image. I don't know why, if we call it the parent, why don't we call it the child? I don't know, but these are questions I have. All right, so let's talk about this. What does f of x What did we say that variable got replaced with?
Y.
Y. So if you were to look at this, what is this? This is 2y. 2y. What math are we doing in between the 2 and the y? Timesing by 2, right? So if it's 2f of x, that means it is a vertical stretch okay, so I'm going to underline that by a factor of 2. That's the language we use to say what we multiplied those y values by. So by a factor of 2. And all that means is we take the y values multiply them by 2. That's all that means. So a vertical stretch means we're going to do this. Okay, now there's a different word that we use. What if I was multiplying by 1/2? What would happen to my shape? We'd times by 1/2, and what would it go this way? It would shrink, right? So sometimes you'll hear the word used, a compression. Okay, like a compression in math by a factor of 1/2. That's just saying that we're not pulling it apart. I've found that using just the word stretch, we're doing a stretch, even though stretch, when we think about stretching, we think about like, I don't know, you guys at home if you can see me do this, but like we're stretching, we're pulling it like apart from each other. That doesn't, the word stretch doesn't always indicate that it's shrinking. Compression does. But if you use the word stretch, that's fine. And we just say a vertical stretch by a factor of 1/2. Just know that that means it's actually getting smaller. Okay? So if we have fractions there, that's going to get smaller. All right, so this is not a mapping rule. This is in function notation. So what happens when it's inside the brackets? Like when we did it yesterday with the slides, what happened? If it was a -2, it was positive, right? So if this is telling me I'm multiplying by 2, it's not telling me the true story. What am I multiplying by?
Negative.
Negatives do something different. You multiply by the reciprocal. So this would be a horizontal. Okay, so you're multiplying the x values by the reciprocal of that value. Sounder's like, no thank you. So it's just, they're multiplied by that reciprocal. So if it's a 2, you multiply by a half. If it was a 3, we'd multiply by 1/3, right? If it was 2/3, what would we multiply by? 3/2, right? So for those of you who are at home not hearing what we're saying, so if it was x, 3/2x like that, we would multiply, so if I did a mapping rule, remember mapping rules tell us our straight math, we would multiply x by the reciprocal of that, so that would be 2/3 x and y. Does that make sense? So when it's inside the brackets, you're multiplying by that reciprocal. So I had a conversation with Himanshu, I think yesterday, about no, maybe it wasn't Himanshu. I don't know who I was talking to about it. No, it was Jacob. Sorry. So we were talking about absolute value graphs in grade 12. And absolute value graphs were in your chapter 7 in grade 11, if you can think back that far. For some of you, it's not as far, but for some of us, it is far. We never really learn the absolute value graphs again, or how to graph absolute value graphs. We'll do it as a practice, but it's like we never revisit it. And the only thing I'll ask you to do is do transformations on an absolute value graph. And I'll never talk about absolute value graphs. So that's a little alarming. So at some point, we'll go through and we'll remember how to graph an absolute value, and then we'll do some transformations on it, okay? All right. Oh, I guess I could have put these on there. Oh, look what I did. Okay, so this is the original function. This is f of x. This is kind of, and so what I did was I put the original function on there. So what I want to do now is I want to sketch 3f of x. So this is kind of like the homework you guys did yesterday. I've given you a funky graph. It's not a function, but I'm asking you, what is this telling me to do? It's telling me to times the y values by 3. I always find that when I'm doing transformations, I like to put little notes, because we're going to do combinations. That's 1.3. I actually think I'm not going to put those on your quiz. I think we'll just do a quiz of 1, 2, 1, 3. Maybe I will. I don't know. I'll make a life choice after today, I promise. So when you do this, when we have combinations, I just go through my equation and I just start writing on it. Okay, y values by 3, x values by 1/2, you know, just to keep it right in my head when I'm going through and doing that. So I'm just going to look at the coordinate pairs, these key coordinate pairs on that one. So on the f of x graph, this point here is -2 and 0. This point here is -1 and -1. Then I go up to 0, 0. Then I go up to 1, 1. And then I go to 2, 0. Oops, sorry guys. So that's my original graph. So if I want to do 3f of x, I'm keeping my x values. So -2, -1, 0, 1, 2. And all I'm doing is I'm taking my y values and I'm multiplying them by 3. Now let's see if I can not screw up this table. 0 times 3 is still 0. -1 times 3 is -3. That's still 0. And this will be a +3, and that'll be 0. Okay? So all I did was I took my y values and I times them by 3. That was the only thing I changed. Okay. I'm just trying to find a color that will actually show up. All right, so now I'm going to plot those points. So -2 and 0, right there. -1 and -3. 0, 0 stayed the same. 1 and +3. And then this one stayed the same. Okay, I got my handy dandy ruler, and I'm going to connect the points. We anticipated, hopefully we anticipated, that this was going to be a stretch, so we're going to get this elongated, it's a vertical stretch, we're going to get this elongated graph. And I'm using rulers to connect my points, and I still screwed up. But you get the idea. There's been no reflections, there's been no changes, it's just this, we've taken it and we've stretched it. Okay, let's talk about invariant points here. What are the invariant points? They're the point that's shared, that's on the original and on the on the image graph, like it has not moved.
All 3 of the 0 points?
Exactly. So, where's my highlighter? So, invariant point, invariant point, invariant point. They're all the ones that didn't get affected by that stretch. And the only number that does that is 0, right? So invariant points are -2 and 0, 0, 0, and positive 2 and 0. These are my invariant points. And we did invariant points with reciprocal graphs in chapter, that was also chapter 7. It was a tough chapter. You guys are like, I don't remember. But if you have your notes and you're looking at those things, the invariant point definition doesn't change. We're just looking at a graph that has some invariant points on it. Everybody cool with that? That's pretty straightforward, right? It's just remembering this one. Multiplied by the reciprocal. It's kind of a pain. Okay, now I see why I put this on here. Okay, so this is again my original graph. Oh, look at that, not even close. This is my original graph. It's the exact same one from the other page. This is the same thing as saying f
Times.
1/3 x. Like if you're not used to seeing it like that, it just means that. Okay, so what's that coefficient? What is this telling me to do? Times by 3.
Make the reciprocal by 3.
Nice. So we're timesing the x values by 3 now, because we're going to do that reciprocal of 1/3. I just want to do a notation for you guys, and you guys can. I see this happen a lot, and this is incorrect. Because my x looks like it's on the denominator, and that's not true. Like, this is incorrect. This is 1/3 times x. So your x shouldn't be sitting either on the top. Well, it can sit on the top, that's no problem. But if it sits on the bottom, it means something totally different. So just be careful, those details again, about where it's located. Just one of those things, I see that happen a lot. So my original table of values, if I remember correctly from the last page, was -2, 0, -1, -1, 0, 0, 1, 1, and 2 and 0. So now when I do this one, it's my x values that I'm going to mess with, and that's going to result in a horizontal stretch. So now we're taking that graph and we're pulling it along the horizontal. We're pulling it apart like the Incredible Hulk. So I'm going to keep all my y values. So those don't change. And then I'm going to take all my x's and times them by 3. Okay, so that's all I did. I find using a table of values, like I said, it really does, like if you're unsure where to go, the table of values is so super helpful. Just make sure you multiply correctly, because I obviously can't on most days. So this is -5, so we're going to go -6 and 0, -3 and -1, 0, 0 stays the same, we go out to 3 and 1, and then 6 and 0. And keep in mind that although it is a stretch, it should still have the same flow as your original graph. And I just did what I said not to do. I'll just change that to an X on top. If you have more than one graph labeled on a coordinate plane, if you have more than one graph, graphed on a coordinate plane, you need to label each graph. Like you need to say which one is what. I know it seems pretty obvious which one is what, but that's kind of that specific detail. So if we were to talk about invariant points with this one, where would my invariant point be? 0, 0. It's the only one that didn't move. So that's my invariant point there. So my...
Wouldn't the another variable point be like, where the lines intersect?
No, because remember, we're not looking at the two lines together. You're looking at you're talking about a solution of a system. We're not solving a system here. Okay? But you're on the right track. We are going to solve systems. It's going to be super fun eventually. But right now, we're not solving of these two functions, we're asking what point, invariant point, what point hasn't changed between the black graph and the red graph. And that's why it's only that 1 point of 0, 0. But you're right, where two graphs cross, that is their solution. But we're not being asked to solve these graphs. Okay, so pretty straightforward. All right, easy peasy. This is a nice, like, beginner kind of thing. All right, so we kind of talked about this. So here's my parent function, graphed right here. So it has a point at -2 and 0, -2 and 0, and it's got another point at -5 and +3. Everybody good? Okay, so this just means, it's like saying there's a -1 outside of that. So this means we're going to multiply y's by -1. Pretty straightforward. I'm pretty good at this. Well, I've got to be honest with you, visualization is not my strong suit. But what I know is if I'm multiplying the y's by -1, what's going to happen there is my graph is going to flip down. So what am I reflected in? In the x-axis. So this is a reflection right? So I'm multiplying my y's, but what happens when I graph that? So this point, it's -2, 0, it stays the same. And now I'm going to be at -5, but now my y values are negative, so it's going to be at, I feel like these aren't the same. This one is at 5, so this one's 5, 5. I was like, that is not a 3. So if this point was -5, +5, this point here would be -5, and we're only timesing the y values by the -1, so this one would be by -5. So your reflection line, your axis of symmetry, is the x-axis. And just like I showed you here, your thing doesn't have to sit on the axis in order to reflect it. It can be anywhere, right? And it will have that reflection. Okay, pretty straightforward. So anybody gonna, oh, what's the invariant point on this one? The -2, 0. Because again, the -2, 0, if I multiply 0, it's the only value that you can multiply it by anything and it still saves itself. It's the only value that works like that. So this one, we're multiplying by the x's. This is like saying -1. What's the reciprocal of -1? I'm shaking my head no. So if I have -1, oh, you can't even see that. I drew that up.
It's still going to be 1 because it's going to be positive. You can't have the...
It's not, okay, so I'm shaking my head no because you guys are all right. You're almost right. You're on the right track.
It should be -1.
It still is -1 because if we change -1 to a fraction, that's going to be -1 over +1. What's the reciprocal of this?
Negative.
So it would be a +1 over -1. Isn't that the same thing?
Yes.
Right. So we're still multiplying by the reciprocal. It just happens that the reciprocal is the exact same thing as the original. Only happens with the number 1. Multiply x values by -1. So if we do that, if we're at -2 and 0, and we are at -5 and 5, so my x values are going to be multiplied by -1. So this -2 is going to be +2, and my -5 is going to be +5. Oh, see, when I don't use a ruler, things are starting to look a little sketchy. Are there any invariant points on this graph?
No.
None. right? So not all graphs have invariant points. Just you need to be able to identify them when you do have them. It's the point that doesn't move. All the points moved on this one. And we would say that this is a reflection in the y-axis. So now my axis of symmetry, that's my mirror. Please note that I drew it in with a dash line. That means that it doesn't really exist on the graph. But you can see that it doesn't have to touch it, but it is an actual reflection in it. Make sense? You guys don't have to put your nose against the glass in order to have your image reflected, right? Oh, there's still more to do. Jeez Louise. Okay. All right. Write an equation formed by reflecting f of x over the x-axis and f of x over the y-axis. I've given you the equation this time, so this is completely different. What do we do when we are reflecting over the x-axis? What math are we doing?
Change the y.
The y's times -1, right? So when we're reflecting over the x-axis, we're taking our y values and timesing them by -1. So we could say negative f of x equals 3x minus 4. Would I ever leave an equation like that? Would I ever leave an equation with a negative y? No. So what am I going to do? I'm going to divide this side by -1 and divide everything on this side by -1. So this is going to be a positive f of x equals a negative 3x plus 4. Make sense? Clear as mud? Perfect. So the y-axis, if I want to reflect in the y-axis, what do I do? Right, so x multiplied by -1. I'm writing the word times. I don't like that word. Multiply is a little bit longer, and I don't want to use a symbol because it gets a little bit cumbersome. So my x's, so this is going to be f of x, and I've got a -1 times 3 times x minus 4. So if I tighten that all up, that's going to be a negative 3x minus 4. Very interesting, eh? Very interesting. Very similar equations, and now we're going to graph them all. You guys good with that? 2 -4. Pardon? Because what am I multiplying by? But what am I'm multiplying just the x's. This one doesn't have an x on it, so I don't touch it. It's just the x values that are getting multiplied. We just multiplied the y values by a -1, but that had a bigger ripple effect, right? By doing that. Oh, this was a bad idea. Okay, I'm changing these. These are 4. This is 8. This is 4. This is 8. 4, 8. -4. -8. All right. Sorry, my scale. I got a little excited there. Okay, let's graph that first one. So it wants all 3. You guys remember how to graph linear functions? These are all in nice forms. These are in your y-intercept. So that tells me my y-intercept. So I cross at -4, and my slope is 3 up, 1 to the right. You guys remember that? So 3 up, 1 to the right. So I'm here. 3 up, 1 to the right. I'm there. 3 up, 1 to the right. Okay, and then I'm going to go 3 down, 1 to the right. So I get this nice line. Okay, so that line is my f of x equals 3x minus 4. Okay, that's my original one. Now, if you had no other information If you had no other information other than reflected in the x-axis, you guys would just change all the points, right? This point would flip to, if it was reflected in the x-axis, your y-intercept would flip to +4, right? This point would flip up here. This point would flip down here, right? We're just flipping their locations. If this is up here, it's going to be down here. And if you graphed it, if we graphed this graph, we'd be +4, and then we'd go down 3, 1 to the right. We'd go, no, I messed up, down 3, 1 to the right. That point should be right there, not right there. Then we'd go down 3, 1 to the right. That point should not be there. I don't think I have any whiteout. This is what happens when I don't use erasable pens. Nah, we'll just have to. So now, this is my line. And what you should see is this part of the line, this part here, flipped up to here, and this part here flipped down to there. And there's 2 points that are bad, oh bad. See, the visual part of me isn't good. All right, so now we're gonna graph, we're gonna reflect in the y-axis. So what we anticipate is our black line, this top is gonna go over to this side, and this bottom is gonna flip here. So this is my blue graph. So again, there's my -4. But now it's down 3, 1 to the right. Oh, and then I'm off the graph. So I'm going to go up 3, 1 to the left. 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 Just jab myself. And this one is my, ooh, I didn't label my red one, f of x equals -3x minus 4. And this one is my y equals -3x minus 4. So we've got some invariant points happening at different places. And this is what you guys would expect to see, right? If it was reflected in the y-axis, this part here, reflect it right here. It's just like a mirror, right? So if I was looking at the blue graph, the blue and the black graph together, where's my invariant point? It's that y-intercept, right? It's that point right there. Well, that was not good. And if I look at my red graph, it's where the two lines cross. So that would be my invariant point there. There's no other places that they share. Does that make sense to everybody? Easy peasy? You're like, sure. Okay, so we're gonna make some generalizations. We're gonna make some statements, mathematical truths. All right, if you have a number outside the f of x, what does that do? If the a is a number, if that was 3, what would you do? Times the y values by 3. What does that give you? Right? If my y values are times by 3, it is a vertical stretch. Okay, so that's the type of transformation. It's a vertical stretch by a factor of a. I just don't know what a is. It could be any number, right? Everybody good with that? And so that means we times the y values by a. Right? That's just a general statement. It doesn't matter what the letter A is, what number that represents, that's what you do. All right, so now with the B next to the X, what is that called? What is that transformation called? It's a horizontal stretch. By a factor of 1 over b. Right? Because it's the reciprocal. And we don't know what the number b is, so... And make sure your b's don't look like 6's here, folks, that you realize that this is a generalization. So we're going to times the x values by 1 over b. All right, so if I'm timing my x values by -1, what happens? What is the transformation that happens? No, well, it's not a stretch because it's by a factor of 1, so that means it stays the same. It's a reflection where? In the y-axis. So this is a reflection I was going to say the y-vertex, and that just doesn't make any sense. And this one, if we're multiplying the y values by -1, we have a reflection in the x-axis this time, so it's opposite to what you're multiplying by. So times y values by -1. So if I gave you this, if I gave you that, what do you know is happening? Vertical stretch by a factor of 3 and a reflection in the y-axis. So really what you could do is you could take your x values and multiply them by -3 here. Like do it all, like I wouldn't expect you to stretch it, then flip it. Do it all at once, right? But just know you're going to get that horizontal stretch and you're going to get it flipped along the y-axis. So they start to look really weird after a while because we'll stretch them, we'll flip them, sometimes we'll do both reflections, those sort of things. So is that it? That's it, that's all. So it's just that reciprocal one that's a little bit tricky and not too terrible. So stretches are multiplying, translations or the slides are adding or subtracting, right? So a stretch you multiply, a slide or translation you add or subtract to do that, okay? So order of operations says what goes first? Brackets, but all we're doing is either multiplying or we're adding or subtracting. What comes first? Multiplying, right? So you're going to do all your stretches before you ever slide anything. Does that make sense? That's 1.3, FYI. You just learned 1.3.